Welcome to our lecture on initial boundary value problems. Today we are going to learn how to predict the future of physical systems, from the cooling of a hot metal rod to the vibrations of a guitar string. This is where the abstract world of differential equations meets physical reality. To understand what an initial boundary value problem is, imagine baking a cake. You need the laws of heat transfer, the initial temperature of the batter, and the temperature of the oven walls. In mathematics, the partial differential equation is our main rule of change. But a PDE alone has infinitely many solutions. To find the one unique solution that matches our reality, we must provide initial conditions which take a snapshot of the system at time 0 and boundary conditions which tell us what happens at the physical edges forever. Now that we understand what these problems are conceptually, let us look at the standard model for heat conduction in a metal rod. The formula you see is the heat equation. It tells us that the rate at which temperature changes over time is proportional to how the temperature curves in space. The symbol U represents temperature and alpha squared is the thermal diffusivity, measuring how fast heat spreads. We also define boundary conditions, for example, keeping both ends at 0 degrees, and an initial condition, f of x, which is the temperature profile before any time has passed. Before we solve the math, let us visualize it. Look at the diagram on screen. The horizontal line is our metal rod. The blue ice cubes at the ends represent our boundary conditions, permanently fixing the edges at 0 degrees. The red wave shows our initial condition, the exact temperature distribution at time 0. Finally, the clock represents our partial differential equation, which will take this initial state and evolve it forward in time, subject to those freezing boundaries. With our visual intuition built, let us solve a concrete example. We have a metal rod of length pi. Our governing rule is the simple heat equation, where alpha squared is 1. The ends are kept at 0 degrees and the rod is initially heated into a perfect sine wave shape. To solve this, we use a powerful technique called separation of variables. We assume the final temperature function can be split into two independent pieces, one depending only on position x and the other only on time t. Continuing with our solution, we substitute our separated guess into the heat equation. By dividing both sides by x times t, we get all time variables on one side and space variables on the other. Since space and time can vary independently, the only way they always equal each other is if they both equal a constant, which we call negative k squared, to ensure the temperature decays over time. This gives us a classic second-order ordinary differential equation for the spatial part, whose general solution is a combination of sine and cosine waves. Next, we apply our physical boundary conditions to find the unknown constants. The left end is at 0 degrees, so plugging in x equals 0 makes the sine term vanish, leaving only b, which must be 0. Now, we apply the right boundary condition at x equals pi. Since b is 0, we are left with a times the sine of k times pi equals 0. To avoid the entire rod being 0, k must be a whole integer, which we will call n. Now we return to the time-dependent part of our equation, replacing k with the integer n we just found. This is a simple first-order differential equation. Its solution is an exponential decay function, which perfectly models how heat dissipates into the cold boundaries over time. We then multiply our spatial and time solutions back together, merging the constants into a single constant called b sub n. This gives us the fundamental building blocks for our temperature profile. Finally, we apply our initial condition to find the exact specific solution. We set time to 0, which turns the exponential term into 1. We then compare our general building block to the given initial temperature wave, sine of x. By matching the left and right sides, it is clear that n must be 1 and the constant must also be 1. This gives us our final unique solution, The sine term maintains the arch shape while the exponential term shrinks its height smoothly over time. Let us shift gears to a different physical system, a vibrating guitar string. The governing rule here is the wave equation. Notice it has a second derivative with respect to time, representing acceleration, rather than the first derivative seen in the heat equation. The constant c squared represents the wave speed. Because of this second time derivative, we now need two initial conditions: the starting shape of the string and its starting velocity when released. We want to solve for a guitar string of length pi. Our wave equation has a wave speed squared of 9. The string is tied down tightly at both ends, giving us our zero boundary conditions. It is pulled into a specific shape and released from a standstill, meaning its initial velocity is 0. Using separation of variables again, we can skip the spatial derivation because just like the metal rod, the fixed ends force the spatial function to be a sine wave with integer n. Moving to the time component, our ordinary differential equation now features a second derivative added to a positive constant. This means its solution will oscillate back and forth using sine and cosine functions, perfectly matching our expectation of a vibrating string. The factor of 3n determines how fast it vibrates. We multiply the spatial sine wave and this time oscillation together to create the general formula for any single harmonic vibration of the string. We must now use our initial conditions to find the specific mode of vibration. First, we apply the initial velocity condition. The problem states the string is released from rest, so the initial velocity is 0. Taking the time derivative of our solution and setting time to 0 makes the cosine derivative vanish, leaving only the constant b. For the velocity to be 0, b must be exactly 0. This simplifies our equation significantly, leaving only the cosine term for time. Finally, we apply our starting shape condition. We set time to 0, which turns the cosine term into a 1. We then compare our simplified equation to the given starting shape of 4 sine of 3x. By matching the pieces on both sides, we can clearly see that n must be 3 and the amplitude a must be 4. This gives us our final unique solution. The string has 3 distinct waves along its length, vibrating up and down rapidly over time. Let us summarize what we have learned. Initial boundary value problems are the absolute cornerstone of predictive physics and engineering. By combining a partial differential equation with specific starting and edge conditions, we guarantee a single, unique solution that accurately models reality. We saw how the separation of variables technique translates complex physical realities into solvable mathematical equations. You now have the framework to predict how systems evolve over time within a confined space. Excellent work today.